In this video, we'll look at pyrostress and the effect of temperature and strain rate on dislocation motion, especially the dislocations in BCC crystals. Let's start by looking at what is pyrostress. Pyrostress is defined as the stress level to glide a dislocation at the absolute temperature equals to 0. That means there's no thermal activation to help with the dislocation glide. Pyrostress is also referred as the lattice friction. As the name suggests, larger the lattice friction, more difficult to glide the dislocation. In many cases, the stress that is required to glide the dislocation is less than the pyrostress. The reason is because there are two components contributing to the dislocation glide. One is mechanical, one is thermal. If we are above the 0K, then the thermal activation can help the dislocation glide as well, thus lowering the mechanical part. Mathematically, the pyrostress can be expressed as 2 pi over b squared multiplied by EP, where b is the Berg's vector, EP is the pyro energy, which we'll discuss more in the next slide. To expand the expression, the pyrostress can be also written down as 2g over 1 minus nu exponential 2 pi w divided by b. Here, g is the shear modulus, nu is the Poisson ratio. Just by looking at this expression, we can tell if we increase the size of the Berg's vector, that will lead to a higher pyrostress. Looking at the w, w is the width of the dislocation core. There are two examples here. The example on the left shows a wide core, while the example on the right shows a narrow core. You can see in the wide core, the lattice distortion extended kind of far away from the dislocation core. In contrast, in the narrow core, the lattice distortion is really confined immediate next to the dislocation core. From the equation above, you can see larger W will lead to a lower pyrostress. There is an important note here. The model we had here can only be applied to dislocations with planar core structure. From the dislocation in BCC metals video, we learned the screw dislocation in BCC metals. They have a non-planar core with a threefold symmetry. Therefore, this model cannot be applied to BCC screw dislocations. Talking about BCC metals, let's look at how dislocation glide in them. This should be our good old friend now. For BCC metals, the edge components have much higher mobility compared to the screw components. And this is the energy barrier if we want to directly glide the screw dislocation. The most stable configuration is to have the screw dislocation lying on its energy minimum. Instead of gliding the entire screw dislocation, the smart way is to nucleate those kinks. Once we have those kinks forming on the dislocation, there will be two factors that will determine how exactly the dislocation will lie on the 110 plane in BCC metals, which depends on the value of EP, the pyro energy. The two competing factors are: 1, the dislocation line wants to lie as much as possible on the energy minimum, and 2, the dislocation line wants to be as short as possible. Let's look at some examples. In case A, the first factor dominates because the dislocation lines, they lie on the energy minimum as much as possible, with a very apparent kink here. In example B, the second factor dominates, and you see the dislocation does not lie as much as possible on the energy minimum without an apparent kink that gives you extra dislocation length. Then what gives you the difference? The answer is pyro energy. When the pyro energy is high, that means the energy barrier is high. The dislocations are as much as possible confined in the energy minimum. When the pyro energy is small, the dislocation is more readily spread out on the slip plane. The next question is, how does the kink mechanism be affected by temperature and strain rate? We'll focus on the temperature effect here. Assuming we are at 0K, then the screw dislocation can only glide through overcoming the pyrostress. The kink mechanism cannot be activated because it is thermally activated. Now, let's increase the temperature. As temperature increases, the probability of atomic vibration increases, then the probability of creating kinks increases. And gliding these kinks are much easier compared to gliding the entire screw dislocation. Therefore, higher temperature leads to more kinks generation, which leads to dramatic softening in BCC metals. Similarly, we can infer lower temperature can lead to a dramatic increase in hardness and strength in BCC metals. Accompanying the high strength and high hardness is the brittleness. And this is the fundamental mechanism why BCC metals they exhibit the ductile to brittle transition. You may have noticed we kept emphasizing BCC metals here. How about FCC metals? Do FCC metals exhibit a similar temperature effect? The answer is no. The reason is that dislocations in FCC metals they do not have the double kink mechanism, thus their strength and hardness are less sensitive to temperature. With the knowledge on the temperature effect, we can extend it to the strain rate effect. Again, let's come back to BCC metals. We just learned the nucleation of kinks is thermally governed. If the process is thermally governed, that gives us one more dimension to consider, which is time. With a given probability, longer the time, the more kinks we can generate. Now, let's think about high strain rate deformation. If the deformation happens very fast, there will not be enough time to nucleate those kinks. Some parts of the screw dislocations are forced to directly glide to overcome the energy barrier. Therefore, we can regard high strain rate deformation being analogous to low temperature deformation. In the previous video and this video, we have spent a lot of effort looking at kinks and jogs. In the next video, we'll look at something more general. We will discuss how dislocation lines are generated from dislocation sources.